Hi, I am Lina Roald.
And I'm Carlton Coffran. And in this video, we will continue our discussion of convex relaxations in power system optimization with a discussion of ACOptimal Power Flow. So this 1962 paper on economic dispatch with AC power flow constraints is widely regarded as one of the most original sources of this seminal optimization problem in power systems. Although it's written in French, I trust many of my colleagues that it does actually describe the optimal power flow problem.
So we have to trust them on that because I also don't speak French. So let's get to what is the actual ACOptimal power flow. So generators in the power system have different costs, and we are able to control them and choose which generator are actually going to provide the power that is going to support our loads. So the optimal power problem is really trying to find a setting for the generators which allow us to produce the power we need at the minimal cost. When we try to do this using an optimization problem, so that is really what the ACOptimal power flow is about, the optimization can get too aggressive if we are not careful to make sure that we dispatch the generators in a way that actually take into account the various operational constraints that we have in the problem. So what we do when we formulate the ACOptimal power flow is that we are adding in the AC power flow constraints, we are adding in generators, we are telling the problem how much demand we have and how much power the generators need to be producing. But we also add operational constraints such as generator limits on the amount of power that can be transmitted over a power line, and we also include voltage bounds on the different nodes. So if we go here and we kind of take a look at our power system again, we still have a set of buses, N. On some of the buses we have sinks or demands. We have some generators at some of the buses which are producing the power. We have voltage bounds that are showing us the how large the voltage magnitudes can be at the various buses. And we have a cost function that describes the cost of the generators. So I would like here to point out that for the generators we have a lower bound and an upper bound, which are describing the full operating range of the generators. And for the voltage bounds we have also a lower bound and an upper bound, which are typically something along the lines of 0.9 per unit to 1.1 per unit. So it's sort of centered around 1 per unit as a typical value.
Plus or minus 10% off nominal is
exactly
what that means.
Yes. And then for the edges, we also have an admittance for each of them that describes how easy it is to transport power across the lines. We have a limit to how much power can be flowing over this transmission line. So we are using here a power limit, so it is limited in terms of apparent power across the line. Sometimes people formulate those limits in terms of currents instead, because currents are important for thermal limits of power lines. But here we are going to use the apparent power. We are also going to include an angle limit on the power lines. So we are essentially going to say that, okay, we have a limitation on how large the angle difference can be between two adjacent nodes. So two nodes connected by a power line cannot have a larger angle difference than this. So this is also a typically included constraint. So if you were watching the previous presentation on the AC power flow problem, what is new here is really these quantities. So we are now having those operational bounds. We are not, instead of specifying the generator power explicitly, we are just specifying the bounds. We also have those voltage bounds, and we have this cost function that describes to us which generator costs the most to run. And then we have those limits on the power flow across the lines, and we also have this limit on the angle differences. Okay, so this gives rise then to the ACOptimal power flow problem. So we have these generators and the voltages on each node, which are the variables in the problem. So these are the the quantities that we are able to choose using the optimization. Our objective here is to minimize generation cost, which is represented here through this generate cost function. We have voltage bounds on the voltages. So here we see that on each node we want the voltage to stay within the lower and the upper limits, and note here that this constraint is formulated in terms of the absolute square of the voltages on bus I, which means that we have also squared the voltage limits. We have generator bounds that are describing the upper and lower bounds on active and reactive power generation at each generator. We have nodal power balance constraint that describe the conservation of power at each point or each node in the system. We have the power flow on the lines, which are describing how much power is flowing from a certain node into the line. Then we have the thermal limits of the lines, or the power limits. They can be thermal limits, they can actually also represent stability limits, depending on the type of system. And then finally we have the angle difference limit, that is the last constraint we are considering here. So this is a very stylized version of this ACOptimal power flow problem. It is kind of the simplest version we can give to you here, which is going to allow us to present the convex relaxations. So you should note that for kind of a more realistic model, there are several extensions that might be required. For example, you might want to include bus shunts, which are the shunt elements at the different buses throughout the system. You might want to include line charging, so essentially a pie model for the lines, where we are looking at having like line shunts. And you might want to include transformers. So all of those are very typical elements that should be included in this problem in a practical way.
And I'll just comment that MatPower is a very popular tool for academic studies in power systems, and it adopts a model with all of these different components. So if you want to do an exact one-to-one comparison with, say, MatPower, you do need to think about these things.
Yes, you should be doing that then. And also we should note that when we are looking at this, as long as most of these, for example, the line charging and the transformers, if we are assuming that those are fixed, this is a very kind of, not a very big extension to the formulation we had on the previous slide. And actually for the things that we are doing here, we are going to assume that the bus shunts, the line charging, and the transformers are really constants or parameters in our optimal power flow problem. So this specifically means that we do not include transformer tap changing as our optimization variables. We do not include the settings of FACTS devices or transmission switching as part of this problem. So all of these are important practical problems that are actually active research topics to develop formulations and optimization problems that are able to handle those kind of things, but they are not covered by what we are doing here. So the next thing that is kind of important to think about is the objective function. So really the AC power flow constraints that we have, I have highlighted here in red, they are really a building block in very many problems that are relevant in power systems operation. But there are very many possible objective functions that we can have to represent those different kinds of problems. So sort of the most common one, at least in academic literature, to try and solve is the economic dispatch. It is also a very practically important problem because we really typically want to operate our system in a low-cost fashion, and that is the objective function that we see here. So we are typically trying to minimize the cost of active power generation. However, we could also say, okay, that is not really what we are going to do. In many places, for example, Europe, transmission system operators might be using optimal power flow problems not to minimize the cost of active power generation, because that is taken care of by a market which is operated separate from them, but they might rather be trying to do some changes to the dispatch to minimize losses or optimize their voltage profile. Sometimes it is used more for security assessment or to make the power system more secure. One typical problem would be to minimize the cost of out-of-market control actions, such as generation redispatch, which might be required in order to satisfy the AC power flow constraints if we are given a certain market outcome that was not developed, which was not found taking those constraints into account. And also very many problems do include n-1 contingency constraints, so that is not really an objective function thing, but this is a practical extension which is very relevant for practical operations, is to include constraints that make sure that the system continue to operate properly even if we have failures of single components. And then there are also very many more.
Okay. So I think the important thing here is that this set of constraints is a fundamental building block in lots of problems. So studying relaxations on a stylized, simplified OPF can potentially have broad implications in lots of different problems.
Exactly. So we really, really care about this problem and understanding it, how we can find good solutions to it, because it really enters into so many different types of problems that are practically relevant. Okay, so to recap what we were doing here, we have presented the ACOptimal Power Flow problem, and which included the core equations and constraints for the AC power system optimization. We have also shown that this type of equations and constraints are very relevant for a large number of problems that are used in practical power systems operation. So it is not limited to economic dispatch as the first paper and seminal paper was, but there are really very many different applications which include those power flow equations.
So coming up next, we're going to do a brief discussion of computational complexity, and that's really just to support the discussion on optimization problems and when they're hard and easy to compute. And then we'll give a brief introduction on solution methods for nonlinear programs and ACOptimal power flow type of problems.